Hello guys, this is QED Math, and today we're going to be looking at three quick geometry problems from the AIME. So this is from the 1985 AIME, and this was question 5. And this one is a really nice question about areas and how they're related to side lengths. So let's read this. As shown in the figure, BAC is divided into 6 smaller triangles by 3 lines that pass through each of the vertices and that pass through some point of concurrency P. The areas of 4 of these triangles are indicated. Find the area of ABC, so the big triangle. So what I'll do is I'll let this be equal to X and I'll let this be equal to Y. So now what I can say is if I call this point D, I can say that AD to DB follows the ratio of 4T to 3T. This is just because triangles APD and triangles BPD share the same height. So the ratio of the areas is just the ratio of the bases. Basically, by the relationship half base times height, we can cancel the heights and the 1/2. So we just get the area ratio of the areas is equal to the ratio of the bases. Okay, so that's good. So now what I can do is I can say that the area of APC to the area of CPB is equal to basically 4/3. It's equal to this 4T over 3T, which is equal to 4 over 3. And so basically what I've shown, but what I'm saying is that this area is over this area is equal to the ratio of the side lengths. I'll leave that as an exercise to prove. Maybe as a hint, what I'd note is that a triangle ADC to triangle BCD is going to be equal to 4 over 3. And the area of triangle APD to BPD is also going to be equal to 4 over 3. So try to like equate them and then perform like some ratio. And you'll get that the area of APC to area of BCP is also equal to 4 over 3. So now let's change this in terms of area. APC we know is x plus 80. I'll probably change back to blue. So we know that x plus 84 over CPB, which is y plus 35. 35 is equal to 4 over 3. Let's call this equation 1. Okay, so let's hunt for more equations, I guess. So another one we can use is probably, if we look at APC and APB, we can again use this kind of ratio. X plus 84 over, or this time what I'll do is I'll look at APC and then I'll look at APB, right? So x plus 84 over 40 plus 30 is 70. This is going to be equal to the area of this one, CPE, so area of CPE, which is y, to the area of PBE, which is 35. Again, just following what we did similarly. So x plus 84 over 70 is equal to y plus 35, labeled as equation 2. Now this is very good. We have 2 equations. We can solve for x and y, and then we can easily find the area. So looking at the first equation, cross multiplying at 3x plus 252 is 4y plus 140. So I have that 4y minus 3x is equal to 112. And then looking at the second equation, if I move the 70 over, I get x plus 84 is equal to 2y. So I get 2y minus x is equal to 84. Plenty of ways to solve for this. Let's multiply this second equation by -2 to get -168. Oh, wait, what? Why did I do that? Now this becomes -4y. So -4y plus 2x is equal to -168. And if we add them, we get -x is equal to -56. So x is equal to 56. And if x is equal to 56, 2y would then be equal to 84 plus 56, which is 140. So y equals 70. Yeah. Okay, so we have this thing. So now we want to find the area of the full triangle. So we do 40 plus 30 plus 35, which is 105 plus 84, which is 189. And then plus the x plus y. We found that x plus y is 126. So we have 189 plus 126, which is precisely 315. All right. Let's move on to this next question, which was the 2001 AIME 1 question 4. In triangle ABC, angle A measures 60 degrees and B measures 45 degrees. So let's see, I can probably like I'll try to draw like this, and then maybe like this. I guess that's good for now. This is going to be my angle A at 60, and this is going to be my B at 45. Respectively, the angle bisector of A intersects BC at T. All right, so at some point T and AT is equal to 24. So if it's an angle bisector, I'm going to write these both as 30, and then find the area of the triangle. Okay, so basically, let's see. So first, let me do some angle tracing. I have a 30, I have a 45, so I know that this has to be 105. So I know that this has to be 75. Basically, that's, I think, some exterior angle theorem. And if this is 75, this must be 75 as well. So I guess ACT is isosceles, meaning that this is 24. Let me make that 75 go over there. Okay, so now if this is 24, what can I do? Maybe I can apply some trigonometry. So I see we can use a law of sines in triangle ABC. So sine 45 over AC, which is 24, would be equal to sine CAB 60 over BC. So let's solve for BC. So sine 45 is root 2 over 2, so we get root 2 over 48 is equal to sine 60 is root 3 over 2, so we get root 3 over 2 BC. So cross multiplying 2 root 2 BC is equal to 48 root 3, and then dividing both sides by 2 root 2, you get BC is equal to 24 times root 3 over root 2, which is 24 times root 6 over 2, which is 12 root 6. Okay, so we have BC is equal to 12 root 6. Okay, great. That's actually very good. So now what I can do is I can write this as 12 root 6. And then what I can do is I can immediately use that the area of ABC is 1/2 times ACBC times the sine of the angle in between. I recommend you try proving the property if you're not already aware of it. So ACB is 75 degrees. We found that using angle chasing. All right, so now this is going to be simple, 1/2. So we know all our side lengths. We know AC is 24. And we just found that BC was 12 root 6. And then now sine is 75. So sine is 75. Let's just compute that real quick. Sine is 75. Okay, so sine of 75 is sine 45 plus 30, and then using the angle identity, that's sine 45 cosine 30, which is root 6 over 4, plus cosine 30 sine 45, which is root 2 over 4. So root 6 plus root 2 over 4. Now let's just do the computation. We have 12. This becomes 12, so you have 144 root 6 times root 6 plus root 2 over 4. This becomes 36 root 6 times root 6 plus root 2, which becomes 216 plus 36 root 12, which is nothing but 216 and then 72 root 3. All right, so this is the answer for our area. Let's go back to a problem. It can be expressed as this. We have it like that, find A plus B plus C. So 216 plus 72 plus 3 is going to be 291. Okay, so I guess what we can do now is let's just move on to the third problem. And what I'll do is I'll also present, I guess, kind of like a Euclidean geometry solution to this. Since it's actually another easy solution, this was just my first trigonometric solution upon glance. So let's just go on to this one and then we can move on. So let me try to expand it a little. So circles of radius 5, 5, and 5, 5, 8, and m over n are externally tangent, mutually externally tangent. So that means every circle is gonna be tangent to. Okay, yeah, I anyways draw it out. So and then we want to find the radius of this fourth mutually externally tangent circle. So let's roughly draw maybe something. So this is 5. This is 5. So I'm gonna put this radius of 8 a little bit bigger, like this maybe. So like this, and then this. Where's this next circle gonna go? It's gonna go probably like over here. It's a tiny circle. So we want to find the radius of this circle. So what I'll do is I'll label this O. I'll label this O1, O2, O3. So centers, And then now what I can do is, it's a good idea to connect centers. And since these are externally tangent, we know that maybe any OI, OJ will just be a sum of the radiuses. So that's a helpful thing. So if I connect O and O2 and I connect O and O1, I know that if I call maybe the radius, I'll probably just inflate it up a little bit. I'll call it R. So this is going to be phi. This is going to be phi. And then O02 and O01 are going to be of length phi plus R. And then if I connect O1 and O2, since they're both radius of phi, I know O1, O2 is going to be 10. Okay, now what? So now if I connect O2 with O3 and O3 with O1, I get something rather interesting. So let me just inflate it up over here. So O2, O1, O3. So some of this is 5 plus 8, which is 13. Some of O3, O1 is 13 again, and then this one is 10. So let's try to find the height, because I know what happens is since this is kind of a symmetric, since we have basically two radiuses of 5 and radius is 8, it's symmetric about this kind of like altitude over here. So it's easy to find since this is isosceles, it bisects, so the altitude is 12. So I know that this altitude is 12, but I can come up with it in another way, right? What I can do is, if I consider the triangle O02, O1, this is going to be 10, and then this is going to be 5 plus R, this is going to be 5 plus R. If we were to drop this, this is 5, 5. So I know this height, maybe like OT, is root of 5 plus R squared minus 5 squared, I should say, which is root R squared plus 10R. So root R squared plus 10R is going to be kind of like up to the center O. And then to get from O to, I guess, here, we just add R. And then to get from here to O3, we just need to add 8. Okay, great. So this is now algebra. Let's just rearrange. We get 4 minus R is root R squared plus 10R. And then let's square both sides. So 4 minus R squared is R squared plus 10R. So we get R squared minus 8R plus 16 is R squared plus 10R. And then we have 18R is equal to 16, from which R is equal to 8 over 9. Answer asks us for n plus 10, so our answer is 17. So before we go, let's just, I guess, do that solution to that Euclidean geometry, kind of like a Euclidean geometry solution. So what I'll do is erase all this and use like no trigonometry, because it is helpful to do that once in a while. So in triangle ABC, let's just draw it again. So that looks maybe a little bit better. Yeah, that looks actually pretty accurate. So this is ABC. Again, we know exactly what we're gonna do. The bisector of A intersects BC at T. So this is T, with AT equals 24. The area of triangle ABC can be expressed as this. Okay, so again, 30, 30. Let's do a similar thing. We know that by problem this was 45. So this is going to be 75 because this is just A plus B, or I should say TAB plus ABT. And then 30, 75, that's 105. So this must be 75. Okay, so this is good. So now what I see is I have a 60-degree and 45-degree. So what this should remind you of is 30, 60, 90 and 45, 45, 90 right triangles. And we can see that in general, it's just good to drop this kind of altitude over here. This gives us a 30, 60, 90 triangle, and that gives us a 45, 45, 90 triangle. And in fact, it splits our 75-degree into two very nice angles. It splits it into a 30-degree and it splits it into a 45-degree angle. Okay, great. So now let's maybe call this point D. So ADC is a 30, 60, 90 triangle. So now if this is gonna be, let's see which one. So that's gonna be 24. So AT is 24. 2x. Okay, so what I'm gonna do is again, what I can note is that I can get some information. Since this is isosceles, I know that this is 24. So now, since ACD is a 30, 60, 90 triangle, we know that AD is 12 and CD is 12 root 3. I'll write that over here. Okay, good. Now CD is 12 root 3. We know that this has to be 12 root 3 since 45, 45, 90, it's isosceles, so CD is equal to DB. And then now I think we are good to solve the problem. Yep. So now what we can do is we can find CD squared using a simple Pythagorean theorem. CD squared is nothing but 24 squared minus 12 squared. And then apply difference of squares. 36 times 12. So taking the square root, we get 6 root 12, which is equal to, I guess, we could write that as 12 root 3. Yeah. Okay, so now we have that this is 12 root 3. So we have that the area is 1/2 times the height, which is 12 root 3, times the base AB, which is 12 plus 12 root 3. So now we are almost done. Let's factor out the 12. So we get 12 times 12, 144, times 2, which is 72, root 3. And then we have 1 plus root 3 over here. So we get 3, which is 216 plus 72, root 3. And then again, it's of this form, so add, we get 291. We are done. So hopefully you guys enjoyed this video. I'll probably upload more often now since it's the summer. More hard problems if you guys want. Again, take care, make sure to subscribe. See you guys in the next video.